supposed to be sitting, actually. All right,
I've been
so
sitting all day.
yeah, the reason I sort of semi-volunteered there is twofold. Something happened last night, and I don't want to bring it up. But one of the greatest mathematicians of the 20th century died last night, and that was the most unusual person you ever met. You know? And he basically, he refused to accept Phil's medal, and he refused to accept any honor. And it was so strange. I read his book actually all of the night, and so I was moved.
Who was this?
Alexander Grothendieck. He's known as Nicola Bourbaki, actually.
Known as what?
Nicola Bourbaki. That's him. But it's irrelevant. Okay, so no, he was a topologist. That's why I followed the geometry and everything sort of fall in place. So the reason I want to say that I joined the department in 2006. I never heard Bill given a seminar, and I mean in the physics department. It was really so amazing. But I'll formally introduce. So the first most important thing. So Bill got his PhD from the University of California at Irvine, where he had some strange acquaintances with some strange personalities depicted in that corner. Then he became a research associate at the same place during those happy hippie years in '67, '68. And then become assistant professor at the University of Southern California. So sticking with California, then moved down to South to Georgia. And then he ended up here in 1987. The University of Arkansas became his home. And he's been here since that.
Been in trouble ever since.
Right, so Bill just became a fellow of American Physics Society, got Master Teacher Award, and published a couple of books, but the word couple is really not reflecting what he's doing. And here's my part. So the reason I want to say it, there is something we usually only say when a person is retired, and that's disaster. And in my view, the most important thing for a scientist is to find his or her own voice. This is the hardest part. It's much easier to follow somebody's work. Like you see big things happen and you just do a little bit of thing. And in my life, I actually honestly seen only maybe about 2-3 people who could find their own voice and redefine the physics. And if you look at the, great Greek geometers and philosophers, they were also drawing something on the sand, well, these geometrical lines, and it's the most stupid things that say you're doing some useless thing. And to me, it was a shocking thing when I saw Bill. He redefined the whole physics, not even one piece, like mechanics. We didn't realize in this institution, and perhaps in the community, what happened. But there is a new voice. It's like Feynman was giving his lectures. It was a totally disastrous things, right? And only like 30, 40 years later, we understand this is the treasure for humanity. It's like reading Aristotle's work. And so I seen what Bill has done. It spans from classical mechanics to quantum mechanics to atomic physics. And he has his own voice. So he's the rarest person I've seen who could deliver the unified view, and that's incredible talent. This is the absolute honor for me to be acquainted with a person who's done it in the 21st century. So I hope the time will come. It's not going to happen right away. People say this is garbage, I don't understand it. It's like what it is. But sooner or later it will happen, and at that point, hopefully Bill will still run and enjoy things. With that thing, it's my really honor and privilege to introduce Bill Harter.
I was just going to tell you some dirty little secrets, not a secret of the universe. But thank you, Jack. I appreciate that. I should also introduce my PhD student of the turn of the century, Tyle C. Reimer, T.C. Reimer, who is responsible for getting the Macintosh stuff out of the Macintosh and out to the rest of the world on a website. And all of that is available. Come down, you want to look at some of this stuff and play with the stuff that we're going to play with in this seminar, you can do it. And also all the text lectures and even video of lectures are free, available. So is the Feynman's lectures, by the way. The cartoon over here, I hope you've been looking at it. The basic idea is that I feel the current understanding of relativity in quantum, UAF, it's kind of foggy, but it's also foggy for the rest of the world. If you just look at an article like this from American Journal of Physics, you see they spend the whole article on 9 formulations of quantum mechanics. So it's kind of like a religion. It's a little bit like we have some of the failings that you find in creation science and stuff like that. We're human. So this is an attempt to just get a little bit better than that. And I want to find out how, if we can clarify and simplify, maybe we could get the field to look a little clearer like this. But more important, can we clarify by simplifying? That's the deal that I want to talk about today. Now, some have forgotten that the special relativity and quantum mechanics are very much a story of geometry and light wave motion. And what we're going to review here, we need to review where Galilean relativity really fails. And he's looking worried, you can see. And also where it doesn't. I'll show you a picture of him not looking so worried. And then we need to see how to make sense of this incredible speed limit. Well, it's roughly speaking 300 megameters. Okay, we're going to use frequencies today to divide by 3, so the arithmetic will not be challenging. But before I begin, I want to point out what we're going to do is play with axioms. We're going to take the Einstein pulse axiom and compare it with Mr. Kenneth Evenson's idea, sort of his experiment's continuous wave axiom. We're also going to use inverse space-time to map things out for us. And you'll recognize that, so it's not really new. But Mr. Evenson's on the paper first author, with the last author being a Nobel Prize winner in the subject that he was working on. And we're very fortunate today, unfortunate not to have Kenna, but unfortunate to have Vera Evenson, who's sitting on the extreme corner over here. And I think she deserves a little bit of a hand. She's a scientist herself, but she is the energy behind Ken. And she has braved ice storm to get here. Okay, here's Albert. Einstein pulse wave axiom. Trains, all different speeds. PW speed, PW pulse wave, lightning flash, seen by all observers to be seen. This is a showstopper. It's a case where cartoon physics becomes a reality. And we need to understand what that really involves. The idea that a pulse could be running along here at a speed that I not only can't catch, I can't begin to catch it. The basic idea of the Galilean relativity is that if I see a group of people that I want to get moving, say at 3 miles an hour that way, I can do it very easily. I simply start walking myself 3 miles an hour this way. There you are, you're all moving now. And so is, according to Galileo, everything in the universe has had 3 miles an hour in that component added to it, until I run into the wall and knock myself out. So that idea is so amazing, and it was amazing at the time. But there's something that completely screws it, and that's light. I didn't add anything to any of the light that was going in this direction or that direction. That's extraordinary. How can we get our head around that? That's, as I say, a showstopper. I make fun of it by calling the Roadrunner axiom. It's as though I'm the coyote, and here comes this Roadrunner, and no matter what crazy thing I buy from the Acme Corporation, say a rocket-powered skateboard, it does not get me any closer to the speed of that darn Roadrunner. It goes, meet, meet. Then I get something else and try to kill myself with it, and you go, meet, meet. It's always meet, meet. So what are we going to do about that? Now, the other thing about this axiom is it's complicated. A pulse is a very complicated combinations of cosine waves. Now it's true that PW is precisely where the wave is, so you feel comfortable. It's kind of particle-like, it's Newtonian-like. A place for everything and everything in its place, you see. That's our classical feeling we should have. What we're going to do today is use OCCAM'S razor to pull that pulse apart. And this is what EVENSON was doing with all his lasers in his laboratory that was needed to really measure the speed of light to 9 figures or more. And we have an axiom that he used all the time. CW speed for all colors is C. We break it down to one color at a time, one cosine wave at a time, one coherent state wave. CW stands for a lot of things here that are very useful. So we're going to imagine, instead of a lightning flash, a 600 terahertz green coherent physics laser, making a nice wave going out for all these trains. And the thing is that now CW was vulnerable to change. This pulse didn't do anything when you ran past it, at least not anything that was really identifiable like color. So we're going to have a 1 CW wave over here or over there affected to first order by a Doppler blue shift if you're running toward it, or a Doppler red shift if you're running away from it, as those two respectively. Now this brings up methodology. A major objection to relativity / quantum theory is it's the only major theoretical development that starts with second order and quite mysterious and very, 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 very tiny effects. So you've lost your audience on the first day of the course in relativity. Completely. So what we're going to do is let's try doing first things first and start off by dealing with this sucker. Okay, now to do that, we're going to use what I call the keyboard of the gods. Jean-Baptiste Joseph Fourier's space, which includes frequency. You've seen frequency, right? The idea is that I can go onto this keyboard here, an optical musician that I am, and press a button anywhere here and pick the frequency by how high I press on this thing, and I'll get the wavelength right too by pressing different places here. But I have something called a wave number. We need to get used to these two objects before we talk. So this is inverse spacetime. Is the mathematical thing that it is. So as TC is going to have one that you can actually manipulate over there, you can press the keys and make things happen over there. Let's look at the time part. The frequency, hertz, that's Heinrich there. You've heard of him, and everybody used that unit, whether they're physicists or not. But inverse to that is wave period. Most people don't see that, that's something that you don't really see because everything's so fast in space-time, but this is standing still. So that's one dimension, which we call the time dimension over in space-time. And the Greek tau is for time. The nu here, the frequency nu, Greek n for number of waves per second. But I want to shoot that down and just call wave number. That's the number of waves per meter. That's where I'll use the word number, and it'll be quantum number later on. Here we have kappa. Kappa for the Greek k. Well, later on we use k for wave vector by putting 2 pi on this. But anyway, this is Mr. Kaiser that you probably haven't heard of too much. He's got the inverse centimeter, our favorite unit, right? The chemists use this all the time. Heinrich Kaiser, one of the first people to do really work on Fraunhofer lines. Okay, look at the dates on some of them. It's kind of interesting, but I'm not going to dwell on that. Anyway, those are the reciprocal things that we get. We have a lambda for wavelength, that's Greek L, and we've got these two spaces, one with meters per wave, seconds per wave, this period and wavelength. Wavelength's not so foreign to most people. So the idea is that if I've got 4/5 here, I got 5/4 there. If I got 3/2 here, I got 2/3 there. We're going to use fractions all the time, so you can easily do the arithmetic. Okay? So that's what we're working with. The idea is I press and hold that key, I get a wave everywhere. A continuous wave everywhere. CW is what that stands for. And for all time. Now this is a mathematical idea. It's really hard to make an instrumental idea. It's only for the gods. But we have here a picture, and TC has got a picture that she can manipulate. And the idea is, as he makes a dimension bigger over there, it gets smaller on the other side because it's the inverse. Now he's making it small, and it's getting big over on the other side. Now what we're really looking for is that thing that calls velocity. We're looking at what the wave does distance over time. Well, that's its wavelength over its period. So here's the formula for wave speed that we're going to use throughout this talk. And all of the relativity and quantum mechanics can be gotten by doing the geometry of this. It's really almost child's play. In this case, we're talking about 2/3 over 5/4. That's 8/15. The wave speed equals the slope to vertical. Now, this is a Minkowski plot, not a Newton plot. So you've got to turn your head on the side to see a slope. But the advantage of this one right here is that when I have a very low slope over here, that corresponds to low speed over there, where this thing would be up like that. And TC will show you that. When I have a low speed, then the tracks in space-time aren't going that way very much. Just going through time and not making much progress. So that's the low speed. And then as you bring the thing the other way, then you get these speeds that are, well, eventually infinite. We're going to see all of that happening in movies of waves as we go through this talk. So on this side, the wave speed equals the slope to horizontal, what we would call slope. 0 here, infinite there. So this is the road map. This is a control panel for stuff over in space-time. Now we're going to push 1 or 2 buttons. That's all to make quantum mechanics and relativity. So here are the formulas just to review. And we have just understood a little bit about velocity. Now we need to look at what quantization is. Quantization is what happens if you put a wave in some kind of box. Now it's a very simple box, a meter. So I've got to have the wave number k quantized to multiples of a half wave. There she is. That's a guitar string vibrating, if you were thinking of sound. Okay, and then I got 2 of them, then I got 3 of them here. But you've got to quantize these things that way. It's the wave number that's going to be quantized, either a half, or 2 halves, or 3 halves, or 4 halves, you see. Now one of the prices we're going to pay with a box is we're going to get another node over here. And that we'll discuss later on. It's becoming a standard wave if it's a perfect box. Okay, so that's the kappa quantization, which is called first quantization in quantum mechanics and field theory. The amplitude quantization, which we were going to sort of ignore for a long time, is called second quantization. So these 2 kinds of quantization, you see this one is due to being put in a phase space jail. And we'll discuss a little bit of that. We don't have time to go into too much detail there, but we don't have to. This one is like quality, the color. This one's like quantity, number of, I hate to use the word because so many people don't even know, have a foggiest idea what it means, photons. Okay, now here is, as will be shown, light wave velocity is very fixed to this Evenson number. In fact, he got the metrologist to not put a plus and minus on. This is a definition of the meter, and we're still working on getting a 10-figure precision absolute measuring distances. A challenge that we may not reach now, or anybody's lifetime here, but maybe we will. Never say never. So it's convenient to use dimensionless like fractions, V over C. So I divide through by C and I get 1. So that makes these graphs have these units and a slope of 1 for light. Let's look at some of the light we're going to work with today. Mostly the green laser, pretty close to this thing. It's a little higher than this. A beautiful blue green of the Mediterranean is kind of right in there. And that's what this laser, this is what Alice's laser is going to be in our scenarios. So here's per space time. I press the key here. Now I'm sort of stuck on one keyboard. This is more like a mortal keyboard. But we haven't explained why I'm stuck on that keyboard. But anyway, when I do, I get something that's got slope 1 over here too. So that's convenient. And as I go up and look at that unit slope graph on either side with those funny units with the C's in front of them on the x-axis here, on the C in front of T on the time-space axis, I get a wave that goes everywhere for all time. Okay? Now, here's a longer one, and we get a shorter thing over here. This is 1200 terahertz, twice the 600. That's deep into the UV here. Deep, I mean deep on the low side on the UV here, because this is making a short wavelength. This reciprocal idea is very important to this. And there's a bunch of those kinky guys for 1200 terahertz. Here's the other end we're going to work. We'll work half of that. Half of 300 terahertz, which is a nice warm infrared. Okay? A 1 micron wave. Oh boy, that's a nice wave. Okay? UV is really dangerous. Okay, now so these two guys are going to work, but also going to work, this mostly, we're going to have this one going the other way. So we're going to have a negative sign on it, so we'll have a slope that's -1. So it's plus or minus unit slope on either graph. Okay, now, here's a picture of the green wave, and I'm going with it on this direction. This is space and time. I have a trajectory that's less than the speed of light, but it's pretty damn fast. Okay, but it's fast enough to make this red. Now, if you move fast enough this way, then the green wave is going to get redder and redder until it dies. Now, one of the things we're going to show is amplitude is frequency too. So amplitude and frequency are going to Doppler shift equally. And that's something most people don't appreciate. But anyway, go the other way, and it's a double whammy. The green wave gets bluer and bluer until you die. So this is quite a dichotomy here. Okay, so that's the thing we're going to be working with. Now let's clarify Evenson's axiom. All colors go see, how the hell does that work? Okay, it kind of sounds good, but are we really sure we know what's going on? So here we have Alice, who is all spiffied up and got on a spaceship coming at Bob from great distance away. She's millions of kilometers away. But she's got powerful lasers, so he can read her light. And she only is turning on infrared, 300 terahertz, 1 micron. And he's got his receiver out there, his frequency meter, and he's seeing a 600 terahertz half micron. Beautiful green blue. It's more beautiful than color I could find in the palette of this computer. Anyway, Bob Tell is being asked by Alice to look for the wavelength of this light. Can Bob tell that this is a phony 600 terahertz by measuring its received wavelength? That's question 1. Question 2, if so, what phony lambda does Bob see? Remember, it's all vacuum here, no fanciness of a crystal or anything. So we're going to put this in per space time. We're going to say, okay, here's 600 terahertz line. It could be somewhere on that. Where on that line? So it gets out a wave meter, which involves a spatial measurement as opposed to a frequency time measurement, and checks out to see what wavelength he's going to get. Well, is he going to get the wavelength that Alice sent? That was a possibility, 1 micron. You know, but what's the deal here? Well, let's shorten this up and just give the damn answer and explain why. The idea is he's got to get the same thing that a green light would give all the time. There's only one kind of green allowed. The universe is just built by a lowest bidder, so you don't have a whole lot of things to choose from. If you even get 2 of these, you've got an infinite. You see, so we're basically proving Evenson's axiom. So it's red, it's got to be, see, it's got to be on the baseball line here, the 45-degree baseline. Okay? That's the idea. Vacuum can only make 1 lambda for each new, well, we're forgetting about beam orientation, polarization, those are things that we can bring up later. And the answer to question 1 is no. CW light carries no birth certificate. Very similar to our president. Okay? All right. And it's also linear dispersion, and PTC has a couple of things that show that. What I'm saying here is that bluer waves, even 0.1% faster or slower than redder ones, a flash from a 5 billion year light distant galaxy would be dispersed over 5 million years. Goodbye, galactic astronomy, our beautiful work here on black hole galaxies and all that kind of stuff. It would just be a psychedelic smear. We'd never get any information at all. So they all marching lockstep. That's really important, an important way to think about it. So there's a pulse. We've proved the pulse wave axiom is a theorem now. It's not an axiom anymore. So we've taken this to a better level, pedagogically. Okay, so here's the deal. Now let's do an easy Doppler shifted rapidity calculation. We're going to define a thing called rapidity in just a minute here. But the idea is Alice says, hey Bob, and Carla, he's talking on cell phone, okay, read your Doppler shift ratios of to my 600 terahertz beam. And I'm going to give a little notation for that, receiver over source. And this little line here, you can think of it, if you slant it a little bit, it'd be a fraction line, but this makes it very clear. Receiver over source, okay? That's the Doppler ratio. So what we got here? Receiver 1200 over source 600, that's 2 to 1. 1200, 600. Okay, I told you the arithmetic's easy. Okay? This gal here says, oh, well, no, it's, for me, C over A is 2 over 3, 400 over 600. Okay? Now, important point here. Why would we be interested in a ratio? Because light is geometric. Evenson axiom says blue, green, red, all of them march in lockstep like we were just showing there. So all frequencies Doppler shift in the same geometric proportion. Like coming over this way, I'm going to cut for same fraction for both the red and the green and the blue and radio waves, you name it. This is a good way to do it. When I see in a textbook that you've got a Doppler shift that's equal to something plus something, I know the person doesn't know what the hell he's talking about. So, Alice sends 600, Bob gets 1200. If she stops and sends 6 hertz, he gets 12. Same coefficient. That means this is like a group transformation. It doesn't care what's going to be acting on, it's still the same. That's a really important mathematical idea. And also, if it's geometric, we probably want to take the log of it. Now, there's other reasons for doing that, but I'm going to come up to the real reason in just a minute. Rapidity is most convenient. Suppose you have a trillion electron-volt proton and hadron collider. Well, your usual speed of light thing is just a pain in the ass. It's 0.9999999, 598. 9999, it sounds like I'm running for president. Herman Cain, remember that guy? Anyway, here's the, much better. That's 2,131. That's better. But best is a logarithm of that. 7.6. That really tells you a lot about this light. It tells you how far the hadron collider really has to go. You're only up to 7. Maybe 8 if you really give them the benefit of the doubt. Okay? But anyway, for low velocity, this rapidity is the standard parameter, very approximately U over C. So Alice and Bob are at the logarithm of 2. Okay? That's what the rapidity is of Bob relative to Alice. And Carla relative to Alice is 2/3. Okay, now here's something I'm going to go through real fast. If you do a time reversal on one of these things, you switch receiver to source. That means you flip the denominator around. So if I flip that situation, I'm going to have a log of 1/2. I'm going to get a minus 0.69. And this one already is a fraction less than 1, so I get a minus on that one. Now here's a good way, anthropomorphic way to appreciate what rapidity is. You can think of rapidity as R for Romans. It's positive on approach, negative on reproach. Okay? Or you can think of R, for Republicans would think R for riches. Riches coming in, oh, I feel good. Riches going out if they crash the market, not so good. Okay? So this is just to help you get a feeling for these things. Now, she's been asking for Bob and Alice and her. What, Carla? Now, Carla, tell me what your rapidity is relative to Bob. How do you get Carla-Bob relativity? Okay? Really easy. I want Carla over Bob. I already know the Alice numbers for those two. So I just do this. Okay? So I get a product like that. You guys that do quantum mechanics with Brazos kids recognize that there's something similar to this, but it isn't quite the same because it's not unitary. And quantum mechanics isn't either. So anyway, what we're going to do is we're going to take this inverse and make an exponential, okay, for those two things. And what you see is that implies, because the product is the sum of exponents, that the answer is the sum of those two. So that's what's written up there. Carla says, I got Carla to Bob equal to Carla to Alice times Alice to Bob, which is 2/3 times 1/2, which is 1/3. That's indeed the right answer, 4/12. Okay? But this is the rapidity numbers right here, minus 1.0. Minus, we're in Splitsville. They're reproaching. Okay? So that is really neat. And this is part one of Galileo's revenge. Rapidity acts exactly like he thought velocity should. Okay, now how do we measure space and time with light waves? That's what is really cool for this method of looking at things that I want you to do. Let light make its own damn coordinates. Don't put your idea what a coordinate should be. Let it do the job for you. This is true of everything I work with. Try to make it do the work for me. I'm very lazy. So what we want to do is use 2 CW lasers and wave interference geometry. We will be getting Einstein-Lorentz-Minkowski graphs for free. That's the upshot of the first half of this talk. But we first have to understand how that works by looking at phasors.
Bill, can you go back one slide?
Sure.
So I lost you for a second. Isn't caller moving?
Carla.
And
Oh,
Alice moving together?
And that's what we're trying
Aren't they getting closer?
These guys,
No.
there's a,
No.
well, she's headed that, see they're leaning that way with her laser, right? It's cartoon, right? And then this one's leaning this way, so it's really blue shifting off of this. And then the green light that's going on here, this is what Bob would look at, and then he'd pass it on. So
No.
pass it on, you see?
Hang
And
on.
it looks green to us because we're in her frame.
Yeah,
If
hang
I
on.
was in his frame, and that thing was square, I would be seeing 1200 coming out of both things. This would be a purple line.
No, hang on a second. Isn't caller and Alice, aren't those two moving towards each other?
No, see the lines on it? It's her exhaust lines here?
Yeah.
She's really tired.
I see.
Melly, right?
I didn't see her exhaust line.
She's headed that way.
Okay,
So she's really got infrared or near infrared, right?
gotcha.
Okay?
So
That's
she's
sort of the
moving
boundary
fast.
visible.
Okay.
Does that make sense?
I'm with you now.
Thank you for,
Thank you.
I mean, how many people appreciated that question, just out of curiosity?
Yes.
Nobody's
So
spoken
now
for
I
you.
know how to interpret, now I know how to interpret rapidity.
Sure.
Okay. Well,
Is
let's
that consistent with Jacques? Is that your term?
No,
I've never heard
it's
of
just
it.
that
I've never
it
heard of it
receives
before.
such a short shrift in
I see.
everything I've read. I figured I'd do something about it.
Yeah.
Okay, now, this is the other thing that I use. Feynman just started to use these things when he died, so I'm hoping he doesn't kill me. But anyway, the idea is use complex numbers. And I meant to write the complex number stuff up there. But the basic idea of e to the something equal cosine plus sine with an I, that's square root of -1. Okay? Now, the way I tell my students is the imaginary part, and you see you're plotting the real part up, imaginary is a little different from what we usually do, but imagination precedes reality by exactly 1/4 wave. But this saying here is, of course, the mantra for most of the U.S. publicly traded corporations. So the idea here is that we're going to later on put a 2 pi on the nu and a 2 pi on the kappa and make a k, and then the nu, well, people use omega. So I think of this as winks and kinks. Way to remember omega and k, all right? So we're going to use that instead of the old nu and kappa sometimes, whenever we have to play with phasors, because we're worried about the angle, this phase angle. It's so incredible, a part of our lore in science. Basically, this is a gauge, like a gas gauge or a speedometer gauge. A gauge is something that has just one needle, and then after it's gone around one, it's lost. You know, you don't have an odometer. what Ken Evenson did was put an odometer on the phasors so that he could count the damn waves, even if they went around more than once. And they went around a lot more than once. So the other thing I want to point out is when we take this stuff to 3 dimensions of space, we're going to need the crazy thing theorem, which has as a special case of the situation we're dealing in here. You've got to admit that I equals square root of -1 is a pretty crazy thing. That's a crowning jewel of mathematics. That was a useful thing to do. And I spend a whole bunch of time in my classes telling people of the about 30 useful things that does for us as physicists. It's just incredible what it does. But one of the things it does is it says that an exponential of a crazy thing, or we're going to use exponentials again here, for both this and the Doppler shift, an exponential of a crazy thing is 1. If the crazy thing is squared, you get -1, you'll get a 1 here, then you'll get the crazy thing times the sine of that parameter, and here you just get the cosine of that. That's a very nice theorem that you should have in your repertoire. And here is a case of being used in 1843 by Hamilton to make 4 quaternions, counting the unit, and that's what makes up space-time. So this is kind of pawing at the idea, why do we have 4 dimensions of space and time? There's some beautiful logic here that I don't have time to go into right now. But an even crazier thing is to put an I on the crazy thing, 2 crazy things. Well, now it'll square up to +1. These aren't so crazy. You learn these right away in quantum mechanics. They're called Powell matrices. So those are what we're going to use later on. That'll be second talk. We're not going to do much with that today. I just want to point out that that's available. So here we go with a space-time diagram of a wave of 1 micron. And we're going to just put a lot of phasors out in the thing there to show what's going on. The whole idea of having this phase is that you get your speed by simply saying, where's the phase equal 0? Where's the phase equal pi over 2? Where's the phase equal pi? You see, where are the crests and troughs and zeros and all that kind of stuff? So all that stuff is just sitting there, static in space and time. And I make the point that there's 2 extremes here of this diagram. The first one that's obvious, and the one that TC's animation shows, is that the waves, phasors, turn like clocks, making something looks sort of like a cyclic. That's interesting too, but not for us right now. But anyway, those clocks are just standing still in our frame, turning to make the wave go. But the other way, that's this case here, the clock velocities are 0 in this frame, but the frequency is 300 terahertz. The other opposite extreme is the clock velocity is very nearly equal to c, and I'm just dragging a clock that isn't moving through there. So there you have a case where they completely shut down their time by going fast. So the relativity lies somewhere between those 2 extremes. And those 2 extremes bracket what is known as gauge invariance. And that will make your head hurt if you try to make that happen here. So that's not the approach we're going to take. When we come around and use it again, you get all kinds of weird stuff. All right, let's go at the waves. Let's let the waves do the work for us now. Our head is hurting. I'm coming back. Come on here. Alice says, okay, Bob, we're going to hit you from both sides now. And they're all just standing with respect to the other. No, see a square box there means it's not moving. No lines, no exhaust valve coming out of it. Okay, so Carlos says, look out, Bob. And Bob says, yikes. And this is what he is going to see meeting head on. And TC will show you first a wave going to the left like this one. You can see the phasors are just like that, except they're moving. Turning, I should say. And then here we have them both together. And now in the middle, we're making, and Bob says, cool, you guys made me a space-time graph out of real zeros. And that's the thing about a CW, it really knows where it's not. Unlike pulses, which have not information about where they are. So this is very zen. Okay? Now, if you watch this thing move, you see how it works. Most of the time you say, hey, standing wave doesn't go anywhere. What are you talking about? Yes, it does. It really goes anywhere. Every once in a while, the real part is 0 everywhere. So, bang, infinitely fast. bang, infinitely fast. That's how he makes the x-axes, or x-grids. Okay? So we've got waves making us a coordinate system. A coordinate system that in many ways you can count on to do all sorts of things for you. All the geometry is going to come out of this coordinate system as we move, as we Doppler shift. But how do you do the algebra? How do you do that, says Bob. Carlos says, easy. You get zeros of any wave sum by factoring it into phase and group parts. Remember your algebra? Exponentials add. Half sum and half difference gives the first one. Half sum minus the half difference gives the second one. Okay, so we can factor that sum into what we call the phase and group. Now the geometry of why you would take half sum and half difference is shown by looking at what happens when you add the red and the green phasors here to get, in general, they would be going at different speeds, to get a half sum, half difference. Here's a half sum, that's the angle of the sum, and then the difference is the difference. And TC has just put up the picture that I'll show on the next slide here, where we say, okay, I'm going to make the phasor diagram call frequency of number B, the B, Bob, okay, 0. That's a gauge transformation, okay? In this gauge space, I can just declare that this frequency is 0, and that of course means I have to make the other one go much faster to keep up. This is a Galilean transformation in gauge space, and it is perfect 18 figures, as far as we can tell. There's nothing funny. We're not going to get burned again by crazy additions of velocities. This one, we're really sure about. The relativity of frequency. So the two places where Galileo gets revenge. And he's looking a lot happier. A lot happier than when he had to deal with a Pope. Okay? So, this little fail circle here is going to pop up in the geometry. Okay?
So Bill, you said it went bam, real fast. That's because you're saying that it's basically jumping half a wavelength at that moment?
Well, you get two of these bangs every period.
Yeah, so you're saying it's jumping half a wavelength in 0 time.
It's just basically making the real parts 0 everywhere for an instant.
Yeah.
And the name for that in the crazy world of pseudo-quantum mechanics is instant time.
Yeah, but if I was watching the wave,
Yeah.
yeah, I would say it suddenly changed by pi when it goes through that point.
That's
so,
right.
So it'd be jumping half a wavelength in 0 time.
Remember, the phasors are just turning as smoothly as you
yeah,
can be.
I understand.
The thing that's jumping is where the zeros are.
Right.
That's what's going on. Yeah. And we need to track, we're going to be tracking both of those when we Doppler shift. But let's see what the arithmetic of that is, and the geometries are pretty well explained already. But what we've done is we've factored this thing into the a minus b and minus a minus b to give me this guy, and then this guy over here that will pop out from just the product with the a plus. So this is the guy that's it's being summed. But here's a product, you see. And that's what very important, because if either one of these things makes a 0, the other one can't do anything about it. And if this one makes a 0, this one can't do anything about it. That's what's so good about product. So that's why we get the zeros doing just what we want them to do, make a coordinate system. An instanton is what that's the word. No, word. Yeah. I don't think I want to eat any of those. Okay. So here's a geometry in per space time. It's a baseball diamond. Okay? Carlos says, okay, Bob, looks like a baseball diamond. P at pitcher's mound, phase, okay? And G, the group, at the grandstand. And thank you, Woody. Woody's on trip, so he can't be thanked. But that's the G right there. This is the difference between our laser pointing this way that Alice has. That's Alice's laser. And then Carla's laser is this one over here. And see, Carla says, I'm on first base. No, she isn't. She's over there, right, but her laser is pointing to third base. Alice says, no, Carla, you're on third. I'm on first. My laser points right. Yours points left. Okay? I brought that silly thing up so that you get an idea of what the arithmetic is. But the basic idea is, Bob says, the P and G vectors, phase and group, pitcher's mound and grandstand, are scale models of the zero grid in the space-time. But P and G is switched. Well, we remember how that switching goes because it's reciprocal. Okay? We'll get more of that in a very detailed thing later on here. But anyway, remember G slope to vertical is 0. P slope to vertical is infinite, you see, if I turn my head on my side. Okay? But over here, P slope has got infinite pointing. That means it's going to be going infinitely fast. G is sitting here with no slope. G stands still. That's the standing wave. Okay. Good enough. We're getting the... Now I want to point out, PW lasers make baseball diamonds in space-time. They take a lot of Fourier components to do that, and there you see PC has a really difficult animation going there that shows these pulse waves going back and forth according to Einstein's rules that we've now made a theorem out of, and it's making a baseball diamond. Whereas with just one CW, you get coordinate systems. So this is very particle-like. This is wave-like, and we need to get wave-like if we're going to do any quantum mechanics before the talk ends here. So now, our 600 terahertz lasers are now moving left to right, both of them. Both of them the same speed. See, exhaust lines, tipped over boxes, cartooning this situation. Okay? And Bob's in the middle. And Bob knows right away, as Carla says, my 600 laser is going to burn you. It's going to blast you with 1200. That's how fast she's going. She's going whatever is worth a factor of 2 in the Doppler, 0.69 in the rapidity. Okay? And Carla's 600 terahertz laser is going away from you at the same speed. And so, and this is the other thing about time reversal, it has to be just the flip of the two, 1/2 of the 600 terahertz, that's 300. So he's going to see a nice infrared on this side. Doppler shifted to 300 terahertz for him. Okay? But they're both green lasers. Okay, Carla says, okay, Alice says, yeah, I got a really fierce UV. Bob says, sunglasses help. I can see R prime, twice as big, e to the rho equal 2. Okay? Now, Evenson axiom says you've got to stay on the baseline no matter what you Doppler. And then the time reversal axiom, it says that, yeah, you've got to stay on baseline, but you also have to be inverse of that one. Okay? So on that side, the other side there, I'm going to be getting 1/2, but with a minus sign. Okay? Even the minus rho with a minus sign is what we see Carla's laser looking like to Bob in per space-time. Okay? So we got a new baseball diamond. We got a marathon to first base, a short steal to second, a marathon back to third, and then it's a real short steal to home. Maybe that's what the Cardinals needed but anyway, whatever. This is what I'm going to think about. Now, obviously, what we've got to do is take half the sum of these and get something here, and half the difference and get something over there. That's going to be our Einstein-Minkowski graph that we're going to make life give us. Well, let's do the algebra too while we're getting the geometry. Okay? So here is the 2, 2 for this thing, purple, and the minus a half plus a half, I'm getting this. So I'm getting a 3/4 and 5/4 as the coordinates here and here, respectively, of the new pitcher mount. Okay? And it's got an algebraic name. It is the hyperbolic sine, and this is the hyperbolic cosine. In general, for any rapidity, for this particular rapidity, it's the numbers that are up before this slide. And then here's a new grandstand. Okay? New grandstands are just the same numbers that switched around. Now we see why it has to be on the bottom. Okay? So that's really cool. There's the formulas for both of them. Okay? Now, Bob looks over into space-time and says, wow, and this is where TC can actually show you what it looks like on a simulation of these two infrared versus ultraviolet light waves going through there and making a new set of grids, which is Hermann Minkowski's coordinate system, which Einstein refused to use because when Hermann was his teacher, he called him a fat, lazy dog or boy. It's not clear. Daniel Kinnifick can straighten me out on that one. But anyway, when he did that, Einstein was incensed that somebody with a Polish name should be going after a German like that. And, well, we're all human, including Einstein. So a little bit of racism there. Screwed relativity for 100 years. If you'd had those Minkowski graphs in the beginning, people wouldn't have been saying that only 12 people can understand this crap. Okay, so you see the real part of it now. It used to go bang, Greg there, you see? And TC can actually blow this up so that you see a fairly large version of it. And even put in little helper lines. These things are all available for you to play with. But little helper lines there to show the hard part of this is what the phase is doing. Making the x-axis again. But this time it's the x-axis seen by Bob, going at whatever the speed is, and we're going to work that out very quickly. Something you should be able to see already. It's 3/5 c. That's really fast for anybody who works on stuff we work on. Okay? So that's the deal here. So Bob says, wow, that's neat. Again, they get switched. We got to measure this sucker in careful detail. So the next 10 slides, I'm going to build you all the parameters in dependent variables that you need for quantum field theory. First of all, Doppler. Doppler is key. Okay? You start with the Dopplers. Okay, as I say up here. All right? You're going to make a table. You're going to fill up this table both with the phase properties, the group properties, well, and some other stuff. We're going to give numbers for this particular example. Okay? So here's the phase. We're going to start with the phase waves. Looking first at the frequency of the phase wave. Phase frequency. Okay? Well, we got to look on this graph to see that. It's this thing right here. That 5 fours. Okay? 1.25. All right? Okay? Then, I flip that to get the phase period. And that's going to be over there in the reciprocal space. I flip that to get 4/5 phase period, 0.8. Okay? This is tedious, but you need to do this once. Okay? Then I go up there and I get the phase wave number. This is this guy right here. This coordinate right here. 3/4, 0.75. Okay? Hyperbolic cosine in general. Okay? And then I go over there and flip that. 3/4 becomes 4/3. Okay? And that's the way this table is going to be. Everything on this side of the line is going to flip the corresponding thing on this side of the line. Okay? That's the thing that nature does. It makes a hall of mirrors for you to live in. Okay? So the flip of the hyperbolic sign is a hyperbolic cosecant. I don't know how to pronounce that yet. All right. But you know, maybe somebody will need a little help with my addiction. Now, what you're seeing here is the slope as a ratio of the cosinus. That's a hyperbolic cotangent. And the thing about the phase, and this is the thing that you really have to understand, is that this is the guts of the wave, of a quantum matter wave. This is the guts right here. This is the heartbeat. If you're religious, it's the soul and the heartbeat. Okay? This is serious stuff. This is fundamental stuff. Okay? All stuff has this. Okay? And we're trying to nail it down in our heads. Okay? So let's go get the stuff that you can actually see. That's behind the scenes. Let's get the stuff you can see. That's the outside of the wave. What we would call the signal. The other thing we would call by radio carrier. Right? Okay? So, let's go get the group frequency. Okay? The group frequency. That's grandstand. Okay? This frequency axis. There it is. 0.75, 3/4. Okay? Just the inverse of this one over there. Okay? And then the inverse of that, again, is this thing, 4/3. Okay? That's the period of the group wave. Okay? Group wave number. Okay? Going back to this graph, there it is. That's wave number axis. Okay? Hyperbolic cosine again. You see, nature's using all this stuff over and over again. It's really neat. And the flip again. Okay? The wavelength, lambda, 0.8, right here. Getting the picture here? We're almost done with this table. All we need is the group velocity. This is classical Newtonian velocity. The group, the outside of the wave. We actually see it. We can't get at that thing that's always going faster than light. This thing is never going faster than light. It's always slower than light. It's the hyperbolic tangent of rho. Okay? There it is. I'll put something else up here. What's the transformation between the old grandstand Pitcher's Mountain and the new one? Well, just take the new one apart. You get a matrix that's called the Lorentz transform matrix. Okay? You don't recognize it if you haven't been using rapidity. But what it does is it turns relativity and quantum field theory into a one-button calculation on the calculator. All these functions are just sitting there waiting to be pushed. Here's the old-fashioned notation. And what's really funny about it is that of all of these parameters in here, only 2 get discussed. And here's Einstein saying, if you can't explain it simply, you don't understand it well enough. That's right, Al. And you don't. And neither did anybody else follow you because he wouldn't let Minkowski get published. Okay? Now these 2 numbers, first of all, is the Einstein time dilation. And I always worry, well, I see a time contraction here, and then there's a Lorentz length contraction, but I see a length dilation as well. Okay, why didn't they mention those? This always bugged me. Now I see that they weren't very observant. You have to do things in a systematic. Okay? Now we're talking about length contraction 20% here. We're talking about dilation 25, okay, percent. Okay? This is 20% down, that's 20% up. This one is a track, you see, made by the zeros, positive slope zeros. There's a 0 right in the middle, and then there are these 2. And that's the contraction of what used to be 1. It's been contracted. It's been second-order Doppler shifted. That's really cool. Now, what you would then say is, well, wait a minute. Sure, light does this. I know it. Doppler shifts and then second-order Doppler shifts. But that's just light. The laser cavities in there are made out of stainless steel. They're not so ethereal. They're not going to contract, are they? No, they're not so rigid as you should think. Those are made out of light waves too, ultimately. Everything is going to obey these laws. And if it doesn't work that way, then the thing wouldn't be in resonance, right? If the stainless steel of the cavity that was here at half a micron wasn't able to follow for Bob, he would see the laser wasn't resonating, whereas Alice would say, you're a dumbass, it is resonating. You see, that's the sort of logic that's going on here. And it's really deep. Maybe deep in the sense of bullshit? Well, let's go further back in time to Thales, 600 BC. Okay, we're getting to the end of our time before we can get everything here. I'm going to have to rush a little bit. But I wanted to show you, if you were to see 2 frequencies coming at you from different directions, different frequencies, you would do a half sum. That was you bisect their sum, make a circle, and where that circle hit would be the geometrical mean. That's Thales' idea of putting right angles from subtending the diameter. Okay? And you'd also have a half difference right here, which would be the ratio of 4 minus 1 over 2 over 4 plus 1 over 2. 2 cancels. I get 3/5. That's the actual speed that I mentioned before, a number of times over. But here's the key thing, is because of the time reversal axiom, this baseball diamond has the same area as this one. And that's the way it's always going to be, and all the points in that baseball diamond, including the pitcher's mound and the second base and other stuff that's out in the field here, it's going to follow hyperbolas. That's your mass shell. Okay, that's the quantum waves mass shell, and TC is showing you how it stretches as you go to higher and higher speeds either way. But returns to normal baseball volume at the bottom. Okay? Now here's another way to look at it. I'm going to go through this very quickly. This is a book written by Lewis Carroll, not Einstein, Epstein. Okay, we actually had him come here. I invited him here. We used another notation for this thing called the stellar aberration angle he makes a big fuss about. It's a flipped out rho. Okay? Epstein was not interested in the rho analysis at all. His book did not have that. He got one page sort of looking at the old-fashioned formulas. Okay? He totally rejected everything that existed. That's a big mistake. So he couldn't get anything published except this, which he did in his father's print shop. He bought the print shop finally from his father and started printing. He printed some really neat books called Thinking Physics. Anybody study that? Really cool. It was with Hewlett. And it's a very pedagogical thing. But he could get no one to do much with this thing. And the basic idea of what he was doing, his trick was to turn this hyperbolic guy into a Pythagorean, a circular guy. That's his trick. Now I put my own notation everywhere here and showed where the connection is between his secant of sigma and Koch of rho. That's what I wanted to show you, very elementary way to see that. But all of the various famous things he has in there. Doesn't have the other ones because he can't get right with the waves. But the idea is to compare these longitudinal and transverse parameters. That's what they are. And we're trying to get at the Lorentz group, so we're looking at the best parameters, and I really know the angles well. It's this new one that you're going to be wrestling with as we go into this. But here's the basis, geometry and trigonometry that's basing on this whole theory. It uses a secant, which means sword, but you really start with a sine, which means slope of incline. And then tangent means tangent. That's the length of a tangent to that point right there, which if you swing up to here is still a tangent. And then there's another way to see a tangent that's more familiar to trigonometry people, that is bisecting that angle right there. The angle is measured in area. You've got to do that in order to make a connection to this guy, which is the hyperbola. And the sine of the sigma becomes the hyperbolic tangent of the rho. The rho is the area subtended by the hyperbola. And then the tangent line of the sigma becomes the sine. You see, the sine and tangent play footsie with each other. Sine, tangent, tangent, sine. Now here's the secant and the Koch. They play footsie. We don't have them up there yet. But there's another example where the cotangent, cosecant, all those things. These are the trigonometric functions that you're used to in real high school trigonometry. You shouldn't be released to these. They're equal to each other if you do it right. Okay, so that's really cool. And here's the geometry sort of spelled out. I'm going to go very quickly here. But the main point of this is I distill it into what I call OCCAM'S sword. This little sword pattern here is so powerful. What TC is showing is what can happen if you try all these parameters going, positive, negative energy as well as forward and backwards. It's an amazing machine that you've got there. This is really neat. So if you want to do waveguides, now by the way, here are the parameters all with the signals as well. If you want to do a waveguide, say TE mill is the easiest one. There's an open sword for a waveguide that's pretty, got a lot of speed to it. Here's one that's right at cutoff, nearly cutoff. Okay? All the geometry's in there, all the factors that make this thing. That's the group velocity in blue and the phase velocity is the green. We don't need two waves to show it because we've got something bouncing back and forth. Circular waves, same thing. There's OCCAM'S sword sort of hiding right in there. There it is in quite a bit of detail with a whole bunch of other stuff that lets you do synchrotron coloring. Okay? This is just showing you there's an ellipse in there. It's really amazing. I mean, this is really beautiful, sort of 600 BC, well, it's really 300 BC geometry. Okay? Now, I want to use this to get you the quantum mechanics relativistically. I want to use the new phase and the kappa phase, because I discovered when I made it a low-speed situation, the Taylor series gave me a constant plus a parabola in a straight line from either of these two at low speeds. Okay? And then I have our formula for the hyperbolic tangent, and the u over c I said was equal to rho when you're at low speeds. Okay? So what we do is we look at that thing and that thing, okay? And we say, hey, they resemble Newton's formulas for kinetic energy and momentum. Okay? This one's linear with an m, that must be the m, and then there's the same thing being an m right there. With this annoying constant. Okay, we have this annoying constant b here. Okay? But we're going to do that. So we're going to rescale this thing by a scaling factor h. And the reason we're going to do that, we're going to attach it so that we get the right units. I need to get over and get some energy out of something that's inverse seconds for frequency, or inverse meters for kappa. Okay? And I can do that very easily with a single scale factor. So the upshot of this is I get an equation like this, and that HB is very famous. That's the MC squared. That's what this annoying constant is. So we're deriving here very quickly something that looks like and matches the, if you kind of know already about MC squared and kinetic energy. The question is this a lucky coincidence or cheap trick? Maybe, maybe. Let's go for it. Let's put exact rho in there. Okay? Exact nu in there, sorry. With the rho. Okay, full rho. Any speed now. Okay? And we'll use the old-fashioned notation. Okay? Bingo. Energy. The exact formula. Old-fashioned notation. And Planck's law. We did this in less than 5 minutes. It took 5 years between Planck and Einstein. Aren't we smart? 20/20 hindsight. Okay, so that's part of the story. But there's still this guy up here. Okay? Now, one of the things it shows is that I just got the vacuum in. Remember we were taking very good care of the amplitude yet? If you take care of the amplitude, you got to replace the h by h times an integer. Then you have the real Planck's law. Okay? And that's just electromagnetic energy density. And what you're getting here, you see, is motivation for something I was mystified by. Why would we want this to be your probability? And it mystified Ehrenfest, because in his paper he made the probability equal to psi. But then Friendly made it psi star psi. Okay, so they were kind of confused about all this stuff back then. But we've settled on it, and it seems to work, so we don't think about it anymore. But damn it, you should think about these things. Otherwise it's a religion. Now, it's a big worry. This guy looks worried, right? When he was worried. And young. Okay? It's a big worry. Is not oscillator energy quadratic in frequency? What are we doing here with this linear thing for energy? Okay? Harmonic oscillator energy is 1/2 amplitude squared, nu squared, maybe some constants, other constants in there, like epsilon 0, we're talking about like your relativistic oscillator. Okay? Oh, what's the big worry here? He looks worried, right? Okay, well, resolution and dirty secret. E, N, and nu phase are all frequencies. We've just shown that energy is frequency. That's what it is. Phase frequency. Okay? We don't need a name for it. Energy is going to go the way of phlogiston. You see that? It's inverse time. That's what it is. With your scales right, of course. You're going to use MKS units. Okay? Turns out electric field also is frequency. You just keep putting more, what you call photons in there. Okay? And you get more frequency on integer steps. Okay. So that's what you really are talking about here, is a frequency times a frequency. It is this thing is going to Doppler shift just like that thing. And that means the electric field of a plane wave is going to Doppler shift. And it does if you do the complicated calculations. We're just deriving it by very quickness here. And then let's look at this other one where we have the exact expression here for kappa phase. Bingo. This is 21. Okay, 16 years later, finally. This guy, and I always try to get a smile out of these photos I get off of the web. And that's the only one I could find where he's really smart. So he's happy. They finally, after 16 years, figured out that h times kappa, or h bar times k, is momentum. So kinks and winks is what you're talking about when you talk about energy and momentum. And I once had somebody here give a talk, and I asked him, how do you define energy? And the answer was, well, energy is what you need to do work. And then the question is, of course, what's work? Well, it's energy. So you just have a circle going there. And that's not the way we're supposed to do physics if you want to be a theorist. Okay? You don't trust anything, including yourself. Now, this motivates particle normalization, because this is a density. So this is where you get the idea, with two waves that are forming a frame, that n is an invariant. The number is an invariant. No matter how fast Bob or Alice go relative to each other's cavity, they're still going to get the same photon count until you open the door. And then when you open the door, the photon count is going to be Doppler shift. So the 1CW and 2CW, very different. One of them's lonely guy, looking for a date, and the other one's a very happy couple. They haven't married yet. When they marry, they're going to produce positron, electron. And that's what we really want to know about. We want the details of that. We don't just want to get an axiom out of that. We want to make some kind of theorems out of that. Okay, so that's where we're headed. And this is not the way to go. Just look at the bottom of this thing and call it your dispersion. Okay. Throw away MC squared. Just call it 0. You can do that. You can change your frequency. That's gauge transformation. That's fine. I don't object to that. It's just inconvenient and wrong-headed, sort of. But it's not wrong. We've gotten a lot of work out of the Bohr-Schrodinger equation, which, by the way, Schrodinger, I'll put his name on there, I'm sorry, I'll apologize for. Because he really knew that there was a relativity behind us before he directed it. Anyway, I want to show you very quickly definitions of mass. This is, what's the matter with mass? We want to shine some light on the elephant in the space-time room. It says, I matter. There's this rest mass, which is the new guy in town. Newton would never have conceived of that. He never would have conceived of the phase that was hiding inside all of the so-called corpuscle particles or whatever he had. Instead, we've got these new ideas for energy and momentum that are based on the hyperbolic or cosines and sines. And rest mass is a constant. It's invariant. Wow, that's neat. No matter how fast I go, that thing doesn't change. And that's the thing that's got the quantum number of the cavity in it. So it's invariant too. So every time you put more photons in, the cavity gets more massive. Okay, that's really cool. But anyway, here is the momentum mass defined by the ratio of P over U. I mean, momentum is mu back in the old days. Okay, so we're going to put the new values of P and U into that to get this. Bingo. Everyone kind of knows that's the momentum mass that gets heavier as you go faster. So this is not an invariant. In fact, this one goes up exponentially. It's all these exponential explosions that you can expect from relativity because it's a geometrical wave theory. Meanwhile, it goes back to the rest mass, so you don't distinguish the mass too much when you're doing that way at slow speeds. Effective mass. This is Newton's guy. F over A. It's the change in momentum over the change in velocity. So we put in the change of the group velocity and the change of the momentum. That's the differentials of these quantities, okay? And you divide that out. Bingo, cosh cubed, okay, instead of cosh, all right? Limiting cases 3 rows. This really blows up, 3 times the rate. More common derivations just take the group velocity directly. That's a very important formula. That's the effective mass in just plain old velocity terms, okay? So if you're talking about Newton's corpuscles, how much mass do they have? They have a rest mass of 0, they have a momentum mass which depends on the frequency, and they have an effective mass that's infinite. This really makes sense because of Evenson's axiom. Evenson says, I cannot change the velocity. That's infinite mass of the kind that involves Newton's deal, all right? But this is a weird one right here. And you get a number for that one. 10 to the minus 3rd kilograms is the energy density for a 600 terahertz wave with a single photon, okay? Now I'm going to rush a little bit here because I want to make, I was going to do a whole thing on the gauge invariance. I want to show you real quickly here that there's a Legendre transformation coming out of this in just a couple of lines. I get a Lagrangian to go with the thing that I call a Hamiltonian. Okay? And I see I have a sign error right there, but that's right. Okay? So these are, and now he's showing you the geometry over there. He's showing you the hyperbola that represents the Hamiltonian, and the circle right here, which represents the Lagrangian. At least it represents the minus Lagrangian. This sign is correct. Okay, so we're getting all this stuff for free. It's just coming for free. Okay, there's the geometry right there. There's Lagrange's first equation, which is the slope of that line, and then this one, you see how they connect with each other. A beautiful thing. So,
2 minutes.
okay. I can do it in less than that if you want. Anyway, let's go. I want to go back here. This is where we started in the baseball diamond, and let's talk about transitions. They're at 45 degrees. Okay, and TC, go ahead and put up the table of things, because that makes sense for the very end of this thing I'm going through here. What I'm doing is I'm saying I have an initial cavity state of something like this. I lose a photon to a lower hyperbola, okay, which has a different momentum and Hamiltonian energy. Okay, so there's a final moving thing that has recoiled. This is Compton scattering in its first stage. Okay, and there goes the light out that made it recoil. It's kind of a pictorial thing, which has this Feynman diagram. I'm a student of Feynman. I've got to figure out where his diagrams are, and this is the way to draw them. I think he would have really loved seeing this, but I don't know. There were times when I thought I had good ideas, and he would just yell at me. You know how it goes here. Anyway, the yellow photon, which is a hyperbolic sign, is coming out with that particular momentum and frequency, because it is on a 45-degree line. The takeaway point here is that the conservation of momentum and energy is not a mystery now. This is just waves being coherent. They maintain their wiggle count or their kink count or whatever it is. That's a symmetry rule. We really feel good about that. That was the worst part of classical mechanics, is when I say, okay, and this fluid called momentum is conserved. Why? Well, now we're starting to get a little bit of a clue to that. Okay? But anyway, another takeaway point is that the recoil rapidity or recoil velocity of these things, okay, is just given by a Doppler formula, which you turn into a logarithmic formula. And rho is nearly equal to u over c, so it turns into that formula right there. If you're a rocket scientist, you will recognize that. Takeaway point 3, emission photons are analogous to rocket exhaust, not bullets. V burnout equals C exhaust, a specific impulse is what they call it. Logarithm of initial and final. The payload and the rocket had all that garbage and it explodes. Okay? That's pretty neat. But here's a really cool thing. If you pick the Doppler shifts on that table equal to a rational number, which we have been doing, everything in there is rational. So that means that every point on here is a rational fraction. But more than that, it is a map of a finite subgroup of the Lorentz-Poincaré group. And all of the Feynman path integrals are defined by group transformations. And that was a major flaw of Feynman's path integral thing, was that the path integrals were infinite, 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 infinite. They're just uncountably impossible. So you had to play all sorts of games and just pick out the ones you wanted. Here you get to use all of the ones in a context that's a discrete. And I can pick any number out. This is just 3 halves. I pick another number, I get a much finer thing. Or I can just divide this thing in half by drawing lines through there and crossing it. And I get a subgroup that's twice as big. So now I can do field theory with group theory. I think. I haven't done this yet. That's all. Now, normally, I would say that we shouldn't have applause at all for something like this. GC and I are plumbers. Plumbers without a crack, ass crack. And what we're telling you is that we've investigated your infrastructure, that is your wiring, your plumbing, in your nice home. Here we are, okay? And we found it deficient. So I would like you to give a sort of a hog call, but a special hog call, the kind of hog call that you would give after a plumber told you that. And I've been through this several times. And what you would normally say when a plumber told you that your infrastructure needs some work is, oh shit. So I want to hear a hog call. It just says that on 3. But if you have an idea that maybe some of this is right, then what I'd like you to say is, no shit, Sherlock. Okay, ready? 1, 2, 3.
No shit, Sherlock.
I heard a Sherlock, so maybe this makes sense.